Welcome to the tinyML Asia 2020. I'm Hye-jun Yu. I'm a professor of electrical engineering at KAIST Korea and chair of today's session, the plenary session and session number 1, hardware session. And it is my pleasure to be on the technical program committee for the tinyML Asia. I will introduce Tanuj Arora of Arm. His presentation is powering innovation in a new world of AI devices on the edge with micro-NPUs. Tanuj Arora is a product manager in the machine learning group at Arm. He's focused on the embedded market and is currently working on the Ethos U NPU product line. Previously, he has worked at Cisco Systems, optimizing networks for telecom service providers. Okay, it's your turn.
Thank you, Dr. Yu. Thank you for the introduction. Yeah, as just introduced, I'm the product manager for Ethos U micro-NPUs at Arm, and today I will be talking about how we can use the Arm micro-NPUs to efficiently accelerate neural networks on edge devices. So let's get started. I don't think I need to tell this to this group, but AI is transforming everything, and at Arm, AI or machine learning is affecting everything that we do. We're seeing quite a lot of increase in demand in a lot of these applications and use cases like security cameras, smart homes, smart cities, consumer electronic devices, and home hubs. A lot of this is due to the benefits of moving these workloads to the edge. The benefits are fairly obvious at this point. There's bandwidth, benefits, security, reliability, privacy is much better as well when you have these things running on the edge rather than the cloud. A lot of these workloads also have a combination of a pre-processing signal pre-processing element where you're cleaning and conditioning the signal and then moving on to the neural network part. So any solution, any hardware IP that's looking at accelerating these workloads should be a combination of that signal processing and neural network part as well. So keeping that in mind, earlier this year, we introduced our Endpoint AI solution, which consisted of a Cortex M55 and the Ethos U55 micro-NPU. Now, it makes sense to start with one of the most ubiquitous pieces of IP in the embedded space. Billions of Cortex-Ms have been shipped by our partners over the last few years, and if you want to start accelerating neural networks, it makes sense to start with all those billions of Cortex-Ms that are available in the market today. So that's what we did. That was what our strategy was, to be to help our partners through open source software, enable them to run those neural networks on the existing pieces of IPs. And when more performance is needed, more throughput is needed, you can add an Ethos U55 under the same software stack to get orders of magnitude increase in performance. Now, in this scenario, what you can still do is you can run the signal processing element on the Cortex M, whereas the neural network can be accelerated on the Ethos U. Recently, last month, we've announced our next generation of Ethos U processor called the Ethos U65, and I will be talking about both of these today in the next few slides. Ethos U65 is based off of the same architecture and follows the same principles, where you can run again the signal processing on the Cortex M and accelerate the neural network part on the Ethos U, but it increases the performance much further. The software remains the same whether you want to run the neural network on CortexM or Ethos U, and that secures any investment that's made on software development. So let's talk in detail about the Ethos U55, which was the first micro-NPU for CortexM CPUs. The way we envision this is Ethos U55 is working in a system where there is a CortexM and you have flash and SRAM. The application is running on the CortexM, and Ethos U55 will accelerate a fixed set of high compute operators, and anything else that needs to run falls back on the CortexM. In this case, the host CortexMs that we support are the CortexM 55, CortexM 7, M33, and M4. So you will see the Ethos U55 in such systems. The U55 does support weight compression. The compression is done offline, and the decompression is done on the fly. Weight compression in embedded systems is extremely important because the memory available is often limited, and what this does is it compression obviously reduces the size of the network and hence enables running bigger networks. Another benefit is that RNN, LSTM are typically weight load bound, and if there are less weights to fetch, it helps to increase the performance of the network as well. In terms of data types, we support 8 and 16-bit activations, integer 8 and 16-bit integer activations, and weights are always 8-bit integer. Now there are 4 different configurations of Ethos U55, going from 32 all the way to 256 max per clock cycle. And as I mentioned, each of these configurations are you can run a fixed set of operators on the micro-NPU, but anything else falls back on the CortexM. So talking about Ethos U65, which is the latest generation of Ethos U, it's the same architecture as U55. The same concept where a fixed set of operators are running, fixed set of high compute operators are running on the micro-NPU, and anything else falls on the CortexM. But this time you get 2 bigger configurations of 512 max per clock cycle and 256 max per clock cycle. What's new with Ethos U65 as well, that you get a DRAM interface. So it comes with dual AXI and a 128-bit AXI to the SRAM and a 128-bit AXI for DRAM support. Now this enables U65 to read and write from DRAM and be used, this combination of CortexM and U65 be used in a bigger Cortex A class system as well. Obviously, this gives the ability to run any size of network with a combination of SRAM and DRAM. The weights can be stored in DRAM. The activations, for example, can be stored in SRAM, or this can be spilled, the activations can be spilled between a combination of SRAM and DRAM depending on the performance and area trade-offs that we're wanting to make here. So So U65 can be used in different types of systems. On the left-hand side, you can see a bigger Cortex A based system where your application is running on a Cortex A CPU. And when a neural network needs to be accelerated, it gets handed off to this sort of machine learning island of CortexM and Ethos-U, where this neural network can be accelerated. Independently, this can also be used in a CortexM based system very similar to Ethos U55, where you have a system SRAM and flash in a low power embedded system. It can be just used as a bigger config of U55. Now I've covered most of this information in the last 2 or 3 slides, but I thought I will highlight the differences to make it absolutely clear as how these two instantiations of the same architecture differ. With the U55, you get 4 different configurations going from 32 to 256 max per clock cycle, whereas with U65, you get the 2 bigger configs of 256 and 512 max per clock cycle. The U55 is designed for use with low power embedded systems, designed for use with just SRAM and flash, whereas the U65 is designed to be used in bigger high performance embedded systems, where you have SRAM and DRAM, but it can also be used as a bigger config in a low power system as well, which is SRAM and flash. You can see the host CPUs supported for both. With U65, we only support the AXI based host CPUs, so Cortex M55 and M7. And the final difference is with U55, you get 2 64-bit AXI master interfaces, whereas with U65, you get 228-bit AXIs. So what sort of networks are supported in these Ethos-U micro-NPUs? As I mentioned before, both of them support the same operator set, and what that means is that you can run a lot of these popular networks that we see in the market completely on Ethos-U, and nothing falls back on the Cortex-M. Just to give a few examples, DSCNNL, which is keyword spotting, a bunch of popular image classification networks. There's speech recognition networks. These are just examples. You can run a lot of other neural networks completely on Ethos-U, and nothing falls back on the Cortex-M. But either today or in the future, there will be networks where something does fall back on the Cortex-M, and in that case, the operators or layers that do fall back on the Cortex-M can be accelerated in software through the CMSysNN library. And I will be talking about this in detail in the next couple of slides. So let's move gears and see what the software flow looks like when you're trying to run a network on Cortex-M. On the left-hand side, you can see is the host where the network is compiled offline. The right-hand side of the diagram is the target device where you're running the application. So on the left-hand side, you can either train a network in TensorFlow or take a trained network in TensorFlow, quantize it down to 8-bit integer into this TensorFlow Lite flat buffer file. Now we are here using the TensorFlow Lite micro runtime to run this flat file on the Cortex-M. The TensorFlow Lite micro is, as I think this community would know, is a version of TensorFlow Lite specifically designed for embedded systems with extremely low memory. So when a network is being accelerated on the Cortex-M, either the CMSIS and optimized kernels can be used, or fall back to the reference kernels of TensorFlow Lite Micro. Now, CMSIS-NN is a library of optimized kernels that we do quarterly releases. We've been doing that for more than a couple of years now. So if you haven't given it a try, please do. Now, if we add an Ethos-U NPU in the same system, how does the software flow change? As you can see, the basic flow still remains the same. Compiling the network offline on the host and then deploying it through the TensorFlow Lite Micro runtime. The only change on the left-hand side, as you can see, is a block called the NN optimizer. Think of this as a compiler to compile the network for the Ethos U NPU. So what it does is it reads in this quantized TensorFlow Lite flat file as an input. It identifies the graphs that will execute on the Ethos U. It does the compression, it does some optimizations and scheduling, and writes all of this information back into the flat file. Now, when you're using the TensorFlow Lite Micro runtime on the target device, the layers that map to the Ethos U are accelerated on that. If anything does fall back on the Cortex-M, it can still be accelerated through the optimized kernels of CMSIS-NN library. And if those are not available, then there's a fallback to the reference kernels that's available. Now, a point to note here is all of the software that you see on the slide, the Ethos U driver, the CMSIS-NN library, the NN optimizer, all of this is open source. It's available today. And yeah, I would highly encourage you to download it, give it a try. I do have links in this presentation that I will shortly get to. This slide shows what the software flow looks like if the Ethos U65 is being used in a bigger Cortex A class system. Again, the basic flow remains the same. The compilation of the network remains the same as before. What gets added is the communication between the Cortex A and Cortex-M. The Cortex A is running the application and it is sort of handing off the neural network to Cortex-M that's still running the TensorFlow Lite Micro runtime software stack. So to enable this, we do provide a example Linux compatible A-class inference API, a software subsystem driver, and an M-class wrapper application. Now the NN optimizer tool, it's the same tool, but more functionality is added for optimization strategies between the DRAM and SRAM. Now that we've looked at both the hardware and software aspects of the Ethos U NPUs, let's look at what the performance looks like for these parts. So what I'm showing here is performance results on a few different networks on Cortex M4, the M55, which is the latest generation Cortex M, and the 128 max per clock cycle config of Ethos U55. As you can see, there's an exponential increase over previous Cortex M's. And across different use cases, again, these are just a few examples for DSC and NL. You can see 110x improvement. For MobileNet, you can see around 74x improvement and over 250x for wave to letter. A couple of things to note. One, this is the 128 max per clock cycle config. Bigger configuration is available. And two, this increase in performance also translates to quite a similar increase in power efficiency, as you can quickly execute the network and power down the NPU. Now, looking at U65, there are various ways where we can try and analyze the performance uplift. One of the things to do is see how it compares to the first generation U55. What I'm showing here is, again, the performance difference for a few different networks across different use cases. That's keyword spotting, image classification, activity recognition, speech recognition, um, noise reduction, things like that. And as you can see, there's on average, there's a 2.5x improvement in actual inferences per second. A lot of this is attributed to the higher bandwidth that's now possible because you have wider buses to the SRAM, so you can get more SRAM bandwidth, and you can use DRAM instead of flash, which helps to increase the bandwidth there as well. And between that and the higher max per cycle, you see quite a big improvement in performance. Another way to look at Ethos U65 performance is to compare it to a Cortex A CPU, because Ethos U65 will be more likely used in accelerating neural networks in Cortex A based systems. So it's good to understand the sort of performance uplift that's possible in this scenario. So what we have here is a quad-core configuration of Cortex A53 running at 1.8 gigahertz, and comparing that to an Ethos U65 core running at 1 gigahertz. So there's a good amount of difference there. Even with this, you can see a performance uplift of around 12x with the micro-NPU. And what's really amazing is the almost 90x improvement in power efficiency. Yeah. Now we do have a simulation models available for both these parts. You have the link here for the Corestone 300 FVP M55 based, and there's another one which has both M55 and U55, which is the MPS3 based Corestone 300 FVP. Now, as I mentioned before, the Ethos U software is open source, and it's available, and I've added the link here. So with the simulation models and the software available open source free of cost, this does give you a way to start developing the applications, run workloads on these new IPs. So I would highly encourage you to give these models and the software a try, and do let us know if you have any questions. Finally, just to summarize very quickly, with the strategy here is to enable accelerating of neural networks on the existing pieces of IP, and improve the machine learning performance with providing new sets of IPs as well. So you can that allows you to target a wide variety of performance points, that allows you flexible integration, where you can start with a CortexM and integrate an Ethos U under the same software stack with very low disruption. And one of the major benefits is being able to run a neural network under the same software stack, either on a CortexM alone or a combination of a CortexM and U55, and also now extending that capability to the Cortex A class embedded devices with the U65. With that, I want to thank you for your time. Happy to take any questions right now.
Thank you, Tanuj, for the nice introduction about the Ethos NPUs. And there are some questions, and First, two questions are about the power consumption and area of U55 and U65. So U55 and U65 cores, how much power consume running typical networks, for example, mobile net version 2?
So we haven't publicly disclosed exact numbers, but we can set up separate meetings and I can talk about that. We have detailed analysis of many different workloads. We can even model your specific scenarios depending on what sort of memory configuration you have, and we can help you with that as well.
Can you give us the ballpark number? I mean, the 100 milliwatt or 1 watt or whatever.
Well, it varies quite a bit, but these IPs are to be used in extremely low power embedded systems. So I won't quote any numbers right now, but we will be publishing some numbers.
Less than 100 milliwatts.
Of course, yeah.
Okay, and about the area.
The only thing that I would add there is what's more interesting than an average power number. What's more interesting to look at is the energy efficiency number. So
of course.
Look at for microjoules per inference. Those sort of numbers are more interesting, I feel. And we will be publishing something in the public domain, but we haven't done that yet. So sorry.
And how about the area? I mean, for example, 28 nanometer or 10 nanometer technology, U55 or U65, how large is it?
So in 16 nanometer, the area ranges starts from 0.1 millimeter square for U55. And as you can see, you go from there, you add double the number of max, and yeah.
Okay. And another question is, does TFLU need some additional development on the software? Or is default set it up to support Ethos U or whatever?
It does support Ethos U. We've been working quite closely with Google, adding more operators to TensorFlow Lite Micro and supporting our Ethos U NPUs.
So it's default support.
I'm sorry.
I mean, the Ethos and TFLU is in the default mode, you mean?
Yes, it is supported. Ethos U55 is supported by TensorFlow Lite Micro, yes.
Okay. Okay, and thank you very much for your nice introduction. Could you explain the coupling between the CPU and the accelerator? Is there a hardware repurposing aspect with the big and little?
Well, these are memory mapped. The NPU is connected directly to the bus with an AXI interface. There's no big little aspect as of yet. And just reading through the questions, because I'm running out of time, I'll quickly take the next two. I did mention the the simulators. Yes, they are available free of cost. Please visit the armdeveloper.com website to get your hands on it. The hardware is not available as of yet, but you will see silicon based on these IPs coming very soon, early 2021 maybe, or sometime in 2021. Until then, as I said, those simulators are available. Those are available free of cost. So hopefully you can get access to it.
Okay, so please answer the remaining questions after your talk, right?
Okay.
Is
yeah,
it okay?
I can do that.
Thank you very much. Thank you very much. would like to thank our sponsor again, who have made this event possible. Our primary sponsor, Arm, the software and hardware foundation for tinyML. And Edge Cortex with the dynamic neural accelerator architecture and co-exploration engine brings cloud-level performance to the edge. And Sixth Sense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. And thank our partner organizations, SHI as our conference partner, and all of our media partners. And you have found them all listed on our website, tinyml.org. Thank you for joining tinyML Asia 2020 with us today. We look forward to seeing you tomorrow.